Hi, Science2 kiddos. Just wanted to use a few slides to review content from Hewitt chapter 5.7, 5.8. Make sure you're feeling good about this. Chapter 5.7 is all about what's called centripetal force, which is commonly misunderstood. A lot of people think of it as the force that's acting forwards here on the object. In reality, centripetal force is actually the attraction towards the center of rotation. So the book defines centripetal force as any force that causes an object to follow a circular path. And we can often think of that circular path as an orbit. That's sort of the classic example. You can think of the moon orbiting Earth. You can think of Earth orbiting the sun. The centripetal force is that attractive force to the center, which in examples like the moon is the gravitational force from the center of the Earth. But it's that inward pull. That's what centripetal force is referring to. And you could simulate this even just by taking a heavy object on the end of a string, like a yo-yo or something, and spinning it around. You are holding that object at that exact distance from you the whole time, and so that's the centripetal force acting towards you. It can be used to simulate gravity. You might have seen this in science fiction movies or read it in books. If we could maybe get a space station that's circular and get it to rotate at the correct speed with the right amount of force, then the floor of that station would become the support force, right? So on Earth, under normal gravity, if you're sitting in a chair, the support force is provided by the chair, and you feel that by your weight, right? You weigh down on the chair, and the chair is weighing up on you. That's what the support force is. Centripetal force can simulate this by simulating support force. By, again, the centripetal force is acting upwards towards the middle here, and then therefore it's that support force. This force acting downwards, the little person standing there, that they would perceive as weight. They would weigh on the floor. If they sat in a chair, they would weigh down on it. And so that would sort of simulate gravity in a space station. Don't know why we haven't done something like this yet. Probably because we can't really build something perfectly circular or stable in space yet. But I don't know. Maybe that's something they'll have in the future. Hewitt, chapter 5.8, then covers projectile motion. A projectile is anything that has been thrown or released and then continues to move on its own. And we're going to ignore things like wind resistance in this example and just keep it simple. So you really just need to consider two forces, right? You've got the horizontal, which again is this motion here, parallel to the ground, and the vertical, which is downwards. Vertical is controlled by gravity, right? And gravity, again, they kind of simplify this, acts on objects with acceleration of 10 meters per second. In other words, objects falling due to gravity are going to increase in speed by 10 meters per second for every second that they fall. In reality, I think it's actually closer to about 9.8, but we'll just keep it simple at 10. So, and I think there's an error in the image in the textbook, but 1 second of falling means the object is falling at 10 meters per second, 2 seconds, 20 meters per second, 2 seconds, 30 meters per second, and so on. The horizontal force we're going to assume is unchanged. Again, we're going to ignore the wind resistance. And so the combination of these two together creates that parabola, right? That sort of curved path downwards, assuming that, again, you've got both forces acting together. And you can change the shape of the parabola based on the initial angle of the throw, right? So here is an object being thrown more in an upward direction, and the parabola you can see is a slightly different shape from our sort of normal, which is right here. And then here is the object being thrown directly downward, and again changes the parabola. What that also changes is the area of impact. You can see that if an object is thrown in an upwards position, it might be a little bit further away. It might have a greater distance than it did compared to the original, whereas if it's thrown straight down, it might actually have a shorter distance from the original, and that's something you're going to explore using an animation. So anytime we think of an object being thrown, you got to think about what are called velocity vectors, which are essentially these arrows here that show you both the direction and also the magnitude of the force acting on an object. And so the combination of these two things gives us the shape or the path that that object follows. So horizontal forces are always going to stay the same. You'll see that that arrow there never changes. And again, that's not really realistic. There are things like wind resistance and stuff that will have an impact. But the vertical forces is where things get a little more interesting. If you look at the vertical forces, you can see that it starts off very strong in the beginning, but then slowly decreases and then goes to nothing at the very peak of the throw. And so that is sort of where the least amount of energy is, least amount of motion. And then it reverses and starts to act downwards. So here you've got that sort of whatever force was applied to it is sending it upwards, but gravity eventually overcomes and takes control and brings the object back down. So it's interesting to see how those forces change, and that's what creates that parabolic path that it follows. All right, and that's it for those chapters.